So welcome back everybody to today's lesson. We are going to be applying our knowledge of Bohr models to make compounds. So let's get started with how do compounds form? And this is page 95 in your notes. So elements combine with other elements in specific proportions. The proportion is indicated in the chemical formula. Table salt is composed of one atom of sodium and one atom of chlorine. So the chemical formula for salt is NaCl. Table salt is never Na2Cl. In other words, there are never two atoms of sodium and one atom of chlorine in a molecule of salt. So this is where it's really important to be careful with your values, and we're going to get into that later of why it is never Na2Cl, but it's essentially to do with the ratios of the elements to one another. So, knowing what we know about the atomic structure of sodium and chlorine explains why this is so. So if we look at the electron structure of sodium, we can count the total number of electrons shown in red. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 total electrons for sodium. And then for chlorine, actually, we can really just focus on the valence shell. So if you notice here, there is one outer electron on sodium, and we have 7 total electrons in chlorine. Both of these are highly reactive. Sodium is a alkali metal, and chlorine is a halogen. So sodium always wants to get rid of its one extra electrons to allow it to have the full valence shell. And then chlorine also wants a full valence shell, but it's one short, so it's going to take the electron from chlorine. So we know that atoms of metals want to give up electrons to become more stable ions. And we know that atoms of non-metals want to gain electrons to become more stable. So that's what we're seeing here. Na wants to give up its extra electron, and chlorine wants to take up an extra electron to have full valence shells. So in your notes, it asks you to draw models for the following atoms and determine the proportions of each element in its compound. You do not need to replace the element pairs below, but you should double check to make sure they've matched. I'm pretty sure I changed them all over, but you may want to pause here and check in with your notes to make sure it matches properly. So I'm going to start by walking you through how to draw compounds. So the example here, which matches the one in your notes, is lithium and fluorine. So to start off, you don't have to do this part, or you may want to do this on a separate piece of paper because the spot in your notes is a little bit small. I am going to draw my circle, and to save space, I'm just going to write the element symbol inside. I'm not going to worry about the protons, etc. You do need to know this, draw the full Bohr model. But in your examples and in this worksheet, you can just leave it with the element instead of including all three. So from here, lithium has 3 electrons, and this is because it has 3 protons. So I'm going to draw my 2, and then remember that your next shell can hold up to 8, but lithium only has 3. So, and then plus fluorine, which is element symbol F, which has 9 electrons. So we've got 2 in the inner, and then fluorine is a halogen, so it should have 7 in the next shell. And when we draw this, we want to fill it fully with 4 electrons, one on kind of each, one at the top, one at the bottom, one on the right, one on the left, and then you can start pairing them up. So that is all the electrons. So you'll notice that, I kind of do this in red, this electron right here is unpaired. So what's going to happen is this electron right here is going to be given to the nonmetal fluorine. And your end result of this, we draw these brackets, and then inside lithium, which since it's donated an electron, only has 2. Because it's lost an electron, it has a +1 charge, but we don't write the 1, we just symbolize it with a plus. And then for fluorine, symbol is F. Your first shell has 2. And now, because of that extra electron, we have 1, 2, 4, 5, 6, 7. And now you have an 8th electron. And you can symbolize the electron that's added with a little X symbol if you want, or you can do it in a different color, just some way to recognize that that is the electron that was originally from lithium. And this has a minus charge because it has gained 1 extra electron, and electrons are negative. So continuing on with our next example here is beryllium and fluorine. So beryllium has an atomic number of 4, meaning because we're dealing with element or atoms here, it also has 4 electrons. I'm going to start doing the same thing as I did before. So start off with a circle, and I'm just going to write Be, which is the symbol for beryllium. Surround that with these 2 electrons, and then the next 2 are left-hand side. So you have a total of 4 electrons. Sorry, I meant to edit that out. For oxygen, we have a central nucleus symbolized with an O for oxygen. 2 electrons in the first shell. And then the outer shell, because it has a total of 8 electrons, will have 6. So 1, 2, 3, 4, and then we start pairing them up. 5, 6. Beryllium, if you look at it, has 2 electrons in the outer shell. So 1 is going to be donated and pair up with this one, and the other one, which I've drawn up here, will pair up with this electron. So it's donated its 2 extra electrons, and oxygen has taken up those 2 electrons, allowing them both to have full valence shells. So our ending result then, draw the square brackets. You can also draw these after you've drawn the model if you want. Be surrounded by the shell with 2. And because it's given up 2 electrons, it is 2+. Our oxygen is surrounded by 1 ring with 2 electrons. And then you've got your outer ring, which has 1, 2, 3, 4, 5, 6. And then I'm going to symbolize these other 2 in red, 7, and 8. And this has a 2- charge because it has gained 2 electrons. So if you notice here, the ratio is 1 beryllium to 1 oxygen. And beryllium is your metal and oxygen is your nonmetal. So for ionic compounds, if you were to write the chemical formula for this, which we're going to get into later, because of this 1-to-1 ratio, the formula is BeO. So the metal always comes first, and then the nonmetal comes second. So let's look at a slightly more complicated example where that ratio is no longer 1-to-1, like my previous 2 examples. So lithium and oxygen. Starting off, we have our lithium, which is symbolized by Li. Outer ring, looking at the atomic number, is 3 total electrons in our atom. Then we have oxygen, which we've also drawn before. So I've got my inner ring, an O to symbolize oxygen, 2 electrons, and then it has a total of 8, so we've used 2. If you were to look at this, if I take this 1 extra electron, which the lithium wants to donate, and I add it to here, you'll notice that I still have this electron unpaired. So to fix that, we need another lithium atom to come in and offer its electron to the oxygen. We're going to draw another one because remember, overall, we want these to have full outer valence shells. So right now, because oxygen doesn't, we want to add 1 more lithium to donate 1 more electron. So this one will come in and pair here. So our end result then, lithium, which now has 2 electrons because it's happily donated 1. So it's now nice and stable. It now has a plus charge. Our oxygen is also happy as it has a total of 8 electrons in its outer shell, which is full. And then it's got the new, actually I'll just symbolize these with X's. It's got these new extra electrons added in. So it has a 2 minus charge because it's gained 2. And then our other lithium, 2 electrons. Sorry, that one was badly drawn. So now the ratio here is 2 lithium to 1 oxygen. So our chemical formula for this is actually Li2, because we have 2 of them, O. So 2 lithium for every 1 oxygen. So just to point out on that worksheet, this is what you should be drawing in the worksheet. The stuff above is just my work showing how I got there. So this is something that you should do on a separate sheet of paper. This represents your chemical formula that it asks you to make out of those models. So we're going to move on to now categorizing compounds, which is page 98 of your notes. Elements are categorized. So we're going to be working with categorizing compounds, which is page 98 of your notes. So compounds are categorized by what elements they are made of and the type of bond that forms between atoms. So we have 2 types of bonds, compounds that are covalently bound, so a covalent bond, or ionically bound. My last 3 examples that I just showed you are examples of ionic bonds, and this is where the electron is transferred from the metal, which is the positive left side of the periodic table, to a non-metal, which would be on the right side of the periodic table, so it gains a negative charge. Covalent compounds, on the other hand, actually share electrons, so we're going to get into that. So covalent compounds. Electrons are shared between the elements, as we can see in the diagram to the right. There's 2 separate atoms, each with a negative charge or a negative electron on the outer shell. And when they come together, you can see the circles are overlapping, which shows that they're sharing those 2 electrons, and that's what forms the bond between them. So it's formed between 2 non-metals. This is important for you to know. Ionic compounds form between a metal and a non-metal. Covalent compounds are between 2 non-metals. So for example, carbon dioxide. So you can see that in the center where carbon is, its electrons are represented in red, where on oxygen they're represented in blue. So you can see that they're being shared between the carbon and the oxygen, and that's what forms the bond. And this is again all to do with having a full valence shell. Another example is water. So here we can see H2O. So hydrogen only has 1 electron, and because of that, it is very reactive. So the oxygen, which has 6 valence electrons, wants to gain 2. So it bonds with 2 hydrogens in order to fill its valence shell, and this also allows hydrogen to fill its valence shell as well. Notice the ratio of 2 hydrogens to 1 oxygen. And same within carbon dioxide, you see 2 oxygens for one carbon. So the subscript, which is the little 2, is showing you how many you have in a ratio. So moving on to ionic compounds, which were what my previous examples were that I was drawing with Bohr models. So electrons are gained or lost to form atoms. So it is the non-metals that gain electrons and the metals that are giving up their extra valence electron. So you can see that symbolized. The atom on the left is donating its 1 electron to the atom on the right. So it is formed between a metal and a non-metal, or a metal and a polyatomic ion, which we will get into in the next 2-ish slides. So examples include sodium chloride. So you can see here in the outer ring, again, sodium has 1 valence electron, making it highly reactive. It wants to give that up to become stable. So chlorine, which is a halogen, has 7 valence electrons. It wants to gain 1 to become stable as well. So sodium gives up its electron, becoming a positive ion, which is a cation, and then chlorine gains an electron, making it an anion. And notice that second element, when we get to naming of compounds, the ending, which was chlorine, becomes chloride. And this is how you end up with sodium chloride, which is NaCl as a compound together. So examples here, again, are sodium chloride and magnesium sulfate. So we have a few types of ionic compounds. And again, remembering that an ionic compound is between a metal and a non-metal. So we have what are called regular ionics, also known as binary. So a metal used has only 1 combining capacity, meaning it has, the combining capacity refers to the valence electron, and this means that it only has 1 charge possible. So examples of this are zinc, silver, and magnesium. The next type is ionic with Roman numerals, and this is also called multivalent. So this is what I mentioned, I believe, in our previous lesson. But essentially, the metals have more than 1 ion charge. So if we check iron on the periodic table, for example, so on the periodic table, iron has a 3+ or a 2+ charge. Nickel has a 2+ or 3+ charge. And manganese has a 2+, 3+, or a 4+ charge. 4+ charge. This is being contrasted with the last sets of ions, which zinc only has a 2+ charge, silver only has a 1+ charge, and magnesium only has a 2+ charge. So 1 ionic charge, 1 type of combining capacity referring to the valence electrons. Multivalent means more than 1 ion charge. So this term is important for you to know. It will come up a lot next year in Science 10. So just be aware that there are different types of ionic compounds. Metals with more than 1 combining capacity are found in groups 5 through 11. Remember that groups are referring to the columns, so moving up and down on the periodic table. And the image to the side just shows you that if you were to look in the area between groups 5 to 11, you would notice that the elements have multiple charges. So not all of them will, but some of them do. So another type of ionic compound can be involving a polyatomic ion. So instead of a non-metal, a polyatomic ion is used. And generally, polyatomic ions will be a negative ion. So polyatomic simply means that it's made up of more than one thing. So if you were to look at this individually, if you look on the chart to the right, this is a sulfite ion, and it is made up of sulfur and 3 oxygens. The next one is NO3, which is nitrate, and this is made of 1 nitrogen and 3 oxygens. And then the OH is a hydroxide, which is made up of 1 oxygen and 1 hydrogen. So this can take the place, basically a metal can pair with the polyatomic ion instead of the non-metal that we were just working with previously with, say, lithium and oxygen. So ionic and covalent compounds. Ionic compounds are always composed of a metal and a non-metal, and the metal always, this is really important, comes first. And remember, metals are on the left-hand side of the periodic table. For example, NaCl, never ClNa. Ionic compounds may also contain a polyatomic ion instead of a nonmetal. Usually the polyatomic ion is negative. There are a couple that are positive, but you're mainly going to be dealing with the negative ones. So Ca, calcium, combines with carbonate, which is CO3. And what this is made up of is a Ca, which has a 2+ charge, CO3, which has, that is carbonate, and it has that should actually be a 2- charge. That is a typo. So this should actually be 2-. So please fix that if it's in your notes as an example. So it should be CaCO3. And one thing I will show you, this is more for next year, but when we have Ca with a 2+ charge, we never write the 2 and 2 because they're balanced. It just becomes CaCO3. Don't worry so much about this. It's more just in case you were wondering why the charge was +2. If you were starting to make that connection, this is why basically those 2's cancel out with each other because they're balanced. So anyways, that's just a little intro to next year. Don't worry too much about it right now. The covalent compounds are composed of 2 or more non-metals. So the last slide I want to show you quickly is something out of your notes. You're going to be looking at this and identifying if it's covalent or ionic, and then if there's a polyatomic present, you will be using that chart from 2 slides back, which gives you a list of polyatomics. I also gave you this list with your periodic table so that you can use for assignments like this as a quick reference while you're learning them. So CO2, carbon is not a metal, it is a non-metal, and oxygen is also a non-metal. So this means we are dealing with a covalent compound. And then, is a polyatomic present? No, this is just made up of carbon and oxygen. So you do not have to name anything here because there's no polyatomic. The tell for a polyatomic is you're going to have more than 2 capital letters present in your compound. So if you look below, that is sodium nitrate. So that one does contain a polyatomic. So I believe this is where I'm going to cut off for today. So we'll continue with the rest of these notes on Monday. Please follow the schedule carefully. And if you have extra time today, please use this time to catch up on any work that you have yet to finish. All right, thank you.